Good afternoon and welcome to the 23rd Annual Exhibit of Hydrogen and Fuel Cell Technologies. There's developments every year, things change. Fuel cells are innovative technologies. We're looking for markets, of course, and for markets we need access to fuels. Fuels is also a big issue here. Where do we get the energy from? What fuels can we use? We have a specialist in this field. I'll be talking to Anthony Anderson, who is Director of Marketing and Business Development at Precision Combustion Incorporated, and we'll be talking about compact fuel processing systems and solid oxide fuel cell generators. Please welcome with me Anthony Anderson.
Great. Thank you, Brian.
So, how are you, Tony?
So far, so good. It's been a very enjoyable week and a lot of good contacts, a lot of good conversations, and great networking. I think there'll be one or two things going forward that'll be a good business opportunity.
Great. We always love to hear that. I suppose we should, before we do anything else, discussing the complexities, do the simple stuff.
Sure.
Precision Combustion Incorporated, could you describe where it came from, how it developed, and what you guys do?
Sure, absolutely. We're a small business, privately owned in North Haven, Connecticut, United States. Established in 1986, focused on really catalytic combustion, hence the name Precision Combustion is where we started, trying to do things in cleaner ways and using generally fossil fuels in a cleaner and better way, more efficient way. A lot of different catalyst development over the years, from catalytic converter technologies. I've done work for NASA, doing trace contaminant oxidation and absorption, doing, and the reforming started in the 1990s, so doing fuel reforming and processing of natural gas, and various liquid fuels, which has really been our focus, is in liquid fuels, for liquid fuel reforming and processing to convert the fuel into something that a fuel cell stack could use, especially fuel cells like fuel cell systems that could use reforming of liquid fuels and diesel.
We'll certainly get to this device here,
Sure.
but you have a number of products and activities right now that that is, you have a revenue.
Yes, we actually have revenue.
Everyone envies that, of course, because it's a young industry, but
Right.
Could you describe the panoply of products and activities you do currently?
Sure, absolutely. And so we're doing some development for downhole heat and steam generation, so actually doing combustion technologies to help produce oil in a cleaner and more effective way. So that's actually in field tests today. We also have some engine generator technologies that we're developing, converting gasoline engines to operate on military fuels for the military, so they can use cheaper and lighter in weight engines for battery charging, for example, and power generation. A lot of other things a big portion of what we're doing is fuel reforming and fuel processing, of course, but also we're doing work with chemical reactors, typically under Department of Energy type contracts for that. Majority of our revenue is actually, since you mentioned revenue, is actually some from government contracts, but probably 40% or so is actually commercial development contracts. So moving something toward a product, and so we're excited because the downhole heat generation is toward a product, and then the military generators with internal combustion engines will be the next one to follow, and then of course fuel reforming and fuel cell systems will be the next products to follow after that. So we have a nice chain of activity moving forward, and we're growing as a company. We're around 30 to 35 employees for many years. We're up to 40 employees now. We have some recent hires, and we have to hire a dozen more people by the end of the summer. So if you're looking for a position in chemical or mechanical engineering or fuel cell systems, etc.
Raise your hand, please.
Yeah, please raise your hand, exactly.
Okay. Addressing this fuel processing issue, to simplify things, and to talk about, I suppose, where everyone knows the fuel cell technology, of course, at high school or the geeks at universities, they always encounter a fuel cell. First they encounter electrolysis, which is, centuries-old technology, splitting that water molecule and you get pure hydrogen, and then you run the pure hydrogen into a PEM cell and you get the electricity back. Why I mention that, of course, is because the typical expectation for a fuel cell is that it needs incredibly pure hydrogen. Otherwise, you destroy that very expensive cell with all of those precious metals in it, and that would be a shame. Why I mention that is because solid oxide fuel cells have the reputation, at least, and I've always misinterpreted it until I talked to you, by the way. I've been here for 17 years, so that says something about my misinterpretation. Fuel cells, solid oxide fuel cells, operate at higher temperatures, and we think of them as stuff that it just eats anything. It's not persnickety. It doesn't matter what's on the plate. As long as there's a hydrocarbon in it, it will take that. And in fact, you told me, no, that's not the case. So first of all, fuel processing processing, when is it necessary for a solid oxide fuel cell? Are there some hydrocarbons that it just loves to swallow up without any fuel processing? And when does fuel processing become necessary and economically viable, I suppose?
Yes, absolutely. And so, as you mentioned, typically a solid oxide fuel cell can take fuels that like pure methane, for example, or even alcohols, propane and the like, with maybe a little bit of what they call a pre-reforming. But in general, they can take them directly without a problem. When you get to liquid fuels, though, however, fuels like diesel, JP8, gasoline, kerosenes, jet fuels, etc., it's a chicken soup of hydrocarbons within that. All kinds of chemical reactions are happening when you're doing reforming or trying to do electrochemistry with that, and sometimes it can adversely affect it. You can have coke formation, you can kill the stack, for example. There's sulfur compounds in here, and so we have a way to deal with that as well. And so what we're developing is really a fuel reforming and processing. So taking the chicken soup, so to speak, or the diesel or JPA type fuels, reforming that, so with fuel air and steam, and then reforming it. And what's unique about our technology is we have a catalyst technology with patented and trademark called microlith. Think of it as a coated mesh type substrate that we put the precious metal catalyst on there. That microlith catalyst actually converts all the sulfur compounds that are present in those liquid fuels and converts it into hydrogen sulfide. Then we can have in the lower half of the silver that you see down here, that's where we have a sulfur removal bed. So we can use a simple technology like zinc oxide, for example, which is very inexpensive. It captures all the sulfur compounds, and in fact, we have developed the technology to the point now we can go all the way up to 3,000 ppm JP8, and then have it be much less than one, about a half a ppm coming out, which is something a solid oxide can tolerate, at least for a certain period of time.
So this is what improves the diet for the cell that follows this device, basically.
Yes.
Okay.
Yeah.
You mentioned a number of things. One, I almost feel like relieved that sulfur poisoning is an issue for the PEM cell and for the solid oxide fuel cell.
Yep.
So what happens to the sulfur? It goes in and it gets extracted?
Yeah, so what we do is we size the bottom half, the sulfur removal cartridge, basically on your maintenance cycle, or plus also bound by how much weight you can carry or how much space you have to actually put something in there. And think of it as like an oil filter in your car. And so that's the kind of the concept that we're going with, as far as you take it apart, you pull out the cartridge, you put a new cartridge in, and you put it back together as part of your maintenance cycle.
Okay. You mentioned a unique mesh catalyst, and I know you did a presentation at the technical forum.
That's right, yes.
And I always have to add, of course, that if you want the technical details, you really have to visit the booth D33, because the complexity, reducing it here to a conversation is doing some injustice to your technology. Okay. But there's one thing I really understood, and I found this fascinating. The mesh design is a way of increasing the surface upon which the reaction takes place, the catalyst. So what benefit does that have? So
what you can do is there's a couple parts to it, is that you have more geometric surface area for the catalyst to be exposed to the gas stream. But then also, because it has a mesh or a wire type of a form factor, you can have throughputs or space velocities that are much higher than other technologies that you can have. And also, you don't form boundary layers. And so if you form a boundary layer, think of your catalytic converter in your car, looks like a honeycomb. As you're flowing gas to it, there's a boundary layer forming, and so the gas can't get to the catalyst, and so it can't do anything, or at least not very effectively. Whereas ours, there's virtually no boundary layer, and so each piece of catalyst is effectively doing what it's supposed to be doing. So what that results in is you have a more cost-effective solution. You have something that's much smaller and much lighter in weight than other solutions that may be able to do this, maybe not, and so it turns out to be a better overall picture.
So this is a way of reducing the overall footprint per kilowatt of the device.
Right. Oh. And so we basically are focused on doing the harder stuff, which is liquid fuels, as that place where less competition, even though there are many reformer and many fuel processing companies. But then also we focus on not only liquid fuels, but applications where you need to be smaller or lighter in weight. So it's typically either things that have to be moved around in distributed generation, or mobile applications like vehicles, aircraft APUs, propulsion, doing unmanned systems, for example, and that type of thing.
We can actually run through the size and application equation, which is very important, of course, because when we follow the evolution, or at least the marketing, the commercialization of solid oxide fuel cells, the classic stationary dream was that everyone would have one of these in their homes.
Right.
And they'd
Yep.
run it off of natural gas, and people would say, why would you want to do that? And the answer, of course, is that they're 30 to 40% more effective in using natural gas. If you use 30 to 40% less natural gas, that is greenhouse emissions dropping down to an acceptable, that's the climate change.
Exactly. And so, typically when you do catalytic type processes like this, your NOx is going, it's 100% decrease, it's going to zero. And then your CO2, because you're more efficient, is dropping, at least 20%. And so it's just a more effective way to use hydrocarbons as we transition the economy, away toward hydrocarbons, or at least toward only hydrocarbons where we have to, as opposed to where we want to.
And biofuels, of course.
Absolutely, and so we've actually operated this with biodiesel, B20, and the like, and so you get a little bit of a renewable aspect to what we're doing. So we typically would say we're fuel agnostic.
So there's of course broad applications to this, but just to mention the notion of reduction of size and how important that can be, and also the environmental factors. Many of the markets that we get, they start as niche markets and then they
Right.
grow. We still need the numbers for a drop in production costs,
Right.
but if you think of a device like this, I'm just going to mention what bothers me in Berlin, where I live. There's a park, they park trucks.
Sure.
And trucks park, the guys sleep in the trucks, and they watch their TVs, and they play
Right.
with their devices and so on. What happens, of course, they have a generator, and it's a conventional diesel generator that's loud, that produces emissions. And one of the potential markets would be, I would suppose, to create a small size, powerful unit that runs directly off the diesel fuel available on the truck in the first place. You wouldn't have to store a canister of hydrogen. Are you looking towards that market?
Yes, absolutely. And what we're doing is, as far as our commercial development, is we're being funded a lot by the military, and so distributed power at the kilowatt scale, unmanned area vehicles at 2 kilowatts. Some military power and propulsion that'll be 5 or 10 kilowatts on vehicles. And so all of these, whether it's a vehicle, a wheeled vehicle, an aircraft, a marine for boats, for example, we could translate to that having fuel cell range extenders for battery electric hybrids, and also in some industrial applications. And so we have a lot of niche applications that we're trying to develop. But the good news is almost all of those have commercial analogs to them. So once you develop it under the military funding, we can then switch to commercial fuels like diesel, for example, or jet fuels, and then have more volume. When volume goes up, the prices go down. And of course, the military who funded in the first place gets to pay cheaper prices as well. And so it's kind of a win-win scenario that we're shooting for.
I should add, if there are questions from the audience, we'll get to the job searchers later, but if there's questions from the audience, just raise your hand and we'll attempt to answer them. I want to, of course, to address the whole portfolio. This is an interesting device. We can talk about it as something that works with an entire fuel cell system.
Right.
But to point out exactly what you do, you're not a stack manufacturer.
No.
But if I look at the history of stack manufacturers here, those guys don't necessarily produce products that have a commercial value because they're not integrated. They're not adapted to a specific function, and there's always been this problem of the fuel cell designers, the engineers who tweak, optimize, whatever, but they don't really get down to product development and working in commercial environments. You don't do stacks, but you do work on integration.
Yes.
With a view towards commercialization on a large scale. So
Right.
how do you work with stack developers, R&D people, and also with commercial companies already? Do you partner with them? Are you looking for cooperations?
Oh, absolutely, absolutely. And so basically our approach is under confidentiality agreements. We vertically integrate to whatever makes sense depending upon who the partners are. And certainly the stack companies are great, great partners. They're great stack manufacturers. They may not be as experienced in managing the thermal flows and doing the reforming and all the other aspects that have to go with that. And that's where we come in. And so many times we'll partner as a subcontractor with a stack company and other parties, or we'll invert the relationship. And so we have a couple prime contracts that we're also doing today where we're developing an integrated system and then working with a stack company and integrating their stack into our system. Whether we be a manufacturer of the entire system at the end, It's going to depend upon the application. Some things like for military, if you're making 500 or 1,000 units a year, as a small company with 40 people, we'll have much more than that at that point if we're making them. But as a small company, to get to that point, we could certainly do it. However, you're talking for automotive applications where it starts at 500,000 units above, you can't with a straight face say, yeah, I'm going to do that and move forward. And so we're always going to have to partner and do a license. And so we might have a design that we've developed as an integrated system, but then hand that over with a license to a company that's in that field. We may supply, the silver piece here, one component or two components, and they integrate everything else with commercial balance of plant and commercial electronics and the like, and do what makes sense.
Seems to me the more advanced technologies get, the more they return to almost antique fascinations with the stars. It sounds like a big leap, the atomus, of course, for the Greeks, but what I'm getting at is that this technology was revived after its discovery in the 19th century because of our trips to the moon, because of rocket science. The alkaline fuel cells in Russia were all developed specifically to aid the path towards the stars, and of course we have NASA.
Actually, our chief scientists actually developed some of the catalysts that were used in the fuel cells back in the 60s when we went orbiting into the moon and the like. So
okay,
that's
so
kind
this
of a
is
tradition. It's not new, yeah.
This is a historical legend that you've got working at your company there. This is like, don't think of the astronauts, folks. Think of the engineers.
There's always people behind the scenes, yes.
Exactly.
And so we've had, and so going off of that, and when we were back in the late 80s, early 90s, doing some initial work with NASA on trace contaminant oxidation, and that's gone forward with trace contaminant adsorption, so putting zeolites and other compounds on our meshes, and even gone as far as we're doing Sabatier methanation now, so taking hydrogen from electrolysis, combining it with the CO2 that's in the spacecraft, catalytically reacting it into synthetic methane, and they're going to use that for power and propulsion on certain missions, or to actually convert those compounds into something that's more amenable to having to human life and an astronaut and the like. And which, of course, that now it has also application out of the power to gas. It's one other way of doing methanation or methanization for that part of the process, if it makes feasible sense.
Yeah. This almost sounds like a Clean Air Act for the astronauts above.
Yes.
Okay.
Yeah, and of course, for the astronauts, those applications, a full scale is 4 astronauts worth of CO2. So we have to scale up 100 times to make something that's beginning to be industrial compatible.
Mm-hmm. Okay, that is basically one of the questions I wanted to ask, and we're already circling around this. That big history means manufacturing for NASA has been an impetus for development in the industry. Is that going to remain the case? Do you still have the visionaries approaching you and saying, do the impossible, please, we have another 10 years?
Absolutely. Between NASA and then, of course, the military recognizing that what we do with the fuel reforming and processing and actually giving us the opportunity here now, or actually 2 opportunities, and hopefully soon 3. We'll hear in June whether we have another one or not, but actually being a system integrator and going from fuel all the way to electrons, and an application that the military really cares about are multiples.
And of course, the device, I think did you mention it by name, the methanation reactor?
Sabatier methanation.
Yeah, okay. Famous French
French chemist, yeah.
Okay, we have to run through briefly what that is, though. It's
carbon dioxide and hydrogen catalytically combined, and it makes synthetic natural gas, or CH4. And so in the astronauts application, it can be more palatable to have that rather than CO2 levels build up in the atmosphere. But then another applications is they want to be able to take that methane and actually use it as propellant or fuel in future missions.
Okay. So again, it's that cycle of fuel reforming.
Yeah, it's going the other direction, yeah.
Going another direction. This is, again, all of these issues are fundamental. People need to do something with hydrogen because we have renewable energies, and there's a question of methanization there. Fuels are the big debate.
Yeah.
Yeah. So we have to break off, unfortunately, now. We've kind of run out of time. I want to remind people, so those job seekers or those who want more technical information here, they should come to Anthony Anderson. He's at booth D33, which is in that direction.
In that direction with the Connecticut Hydrogen Fuel Cell Coalition area. Mm-hmm. And certainly, if you're more interested in some of the technical details, you can look at the website and see the technical talk from Monday. The video is online now, and you can observe that as well.
Okay. Wonderful. I've been talking to Anthony Anderson, who's from Precision Combustion. He's the Director of Marketing and Business Development there. And we've been discussing compact fuel processing systems and solid oxide fuel cell generators. It's been a pleasure, Anthony, to talk to you. I hope you're back next year.
I hope so, too. I think we will be.
Wonderful.
Thank you.
Thank you, Tony.
Let's appreciate Brian.
And thank you. We have a pause, but we will be returning. So we don't have a pause. Oh no, Ski. I can say it from here. Ski Milburn is going to be up on the stage. Now, he told me recently he has an announcement to make, and he would tell me in advance of the announcement, but he'd have to kill me because it's so important. We'll see if the message matches the announcement of the message, but he'll be on the stage shortly with my colleague. Sorry about that.